So my talk is called Demystifying the Database. So just going to kind of talk about, next slide. Just going to talk about sort of what a database management system is and why you should care. And then we should build an understanding for like what the storage model is for how databases actually do work under the hood. And then I'm going to briefly talk about this toy database that I've started called SmallDB because it's small. All right.
Next slide.
Next slide. So what is a database? Does anybody know? Everybody have any ideas of what a database could be?
Yes.
Yeah. It's what?
It's where all the real business like.
Okay.
It could be as simple as a spreadsheet, right?
A what?
It could be as simple as a spreadsheet.
Yeah, it could be a spreadsheet. Or
Where data is stored and accessed.
yes, it's stored and accessed. So like I guess more specifically, like a database is more like what some people would call a data set, and like next slide, I guess. It's really just a way to like model some system with data. So you might have, movies, like a movie database, or like you might have Wikipedia, stuff like that, right? Those are all databases, but the actual system for managing that database and reading and writing to it, that's where things get complicated. So, yeah. I don't know why that actually came out as separate ones, okay, but, oh yeah, machine learning models, those are also databases too, right?
Oh, right.
They're a set of data, they're a bunch of weights, right? And you can actually query them. Okay, so a DBMS is essentially a database management system. And so really what that is it's a storage layer and it's a query language. So you could sort of think of it as like back-end and front-end, right? So like the back-end is actually like the data structures that are involved that actually store the data. And then the query language is a nice way, it's a nice front-end for you to be able to access that data and modify it. Databases also afford you concurrency control, something that's really taken for granted. So if you think about a traditional web application architecture, you can scale that out infinitely, right? But a database is a lot harder to scale because the concurrency and the access patterns are a lot more unique and they're hard to parallelize. So a database aims to control that concurrency for you. I'm not really going to talk too much about the query language or the concurrency control because I haven't really implemented much of it for myself. So we're really going to talk more today about the storage engine. And also going forward, I think everyone was talking about thinking about databases like DBMSs. So from now on, I'm just going to say database instead of DBMS because that's a lot easier to say. Okay. So why is file.write data complicated? So disks are actually very slow. They're about 100 times slower than RAM. And they also have caching mechanisms. So if you try to write to disk, sometimes they don't actually get there. Sometimes you actually need to flush the data to disk. And so there's a bunch of hardware caches and queues in between, your program, the OS, and then the hardware actually has some caching, and then you actually have your physical storage. So you sometimes need to call fsync on Linux for example, to actually sync everything to disk. Disks are also block addressable. So like typically when you're dealing with a program, you're saying, okay, give me that part of an array, give me that byte of memory. But with a disk, you cannot do that. You have to ask for a specific full block page of memory, and that's very slow and expensive. So you have to be really smart about how you want to actually access the data if you want to be efficient. So here are some types of database management systems. You have relational databases. So you have different relations, and then they have keys that relate to each other. You have OLAP databases, which are primarily used for analytical workloads. So whenever you need to scan a lot of data or you need to aggregate a lot of data, you would use an OLAP system. Document stores, I don't use document stores too often, but they're there. They give you sort of a JSON-like experience on top of your database. Then you have graph databases or entity attribute value stores, if you've ever dealt with that. And then what's popular now are vector databases. So they're essentially ways that you can do semantic searches on vectors of data that you store in your database. So today we're going to talk about relational databases, though, because we're going to be building, or we're currently working on a SQLite clone. So relational databases, just a quick review, is you have relations, which are tables, and so they're basically unordered sets or multi-sets or bags. And so what those are is they have a set of columns, and they have some attribute out of those columns that uniquely identifies them. And that's a relation. And you can have relations that relate to each other based off of the similarity in their keys. So you can have relationships between a primary key, which is a unique identifier for a relation, and then that relation can relate to another key in a foreign relation by a value in one of its domains. Sorry that's not very clear, but basically you have little pointers between these tables here that allow you to join the data and do operations that you would over like mathematical sets. So you could say, hey, give me everywhere that there's an artist that matches this album, right? And then you can join all those together and get all of those as one result. So next slide. So how would you actually clone SQLite's storage engine? So this is sort of like the meat and potatoes here. So it's a combination of mainly two things. There's a pager and there's a B-tree system. So there's a pager and a B-tree system, and there's different types of database pages that you're going to be reading, and each of those are 4 kilobyte blocks that you're going to be getting out. So related to the B-tree, there's a leaf page and there's an inner leaf page. And then there's overflow pages and free list pages, which are, the free list pages are what the pager uses. And then there's, of course, a root page from which all of those data structures can be accessed. So the pager is, it kind of follows this API. You can pretty much just ask for a page by saying read page ID, give me that page. You could write to a page, so you can say, oh, I have this handle, this pointer to a page, I want to write to it. And then you can also append to a page, or you can append a page, which is like, hey, give me a new page and tell me its ID. So it's like, give me a pointer to a page. So you can basically allocate pages. And then you can also free page, it's sort of like deleting a page, right? Sort of like you would with like malloc and free in like a C-like programming language. A page is like a block of memory. So like SQLite does everything in a single page. So whenever you're asking for a page, you're sort of treating a page as like a pointer. So it's like, I have this ID for a page, it's like a handle, and then whenever you ask the pager, it'll give you that full page back whenever it's ready to. So this will be a little bit easier to understand whenever you start seeing some pictures here. So I guess next slide. So this is really more what I'm talking about. So this is like how you would implement like a naive database. You just have a bunch of pages that are linked together and say you want to find someone's name. So you would just read page 1. Hey, is it in page 1? You scan through all the data. Is it in page 1? Oh, no, it's not. Okay, go to the next one. Go to the next one. But as that scales, it gets really slow. So this will not work. So what we have to do something a little bit more clever. So I guess next slide. This is more talks about like how actual tuples, like the rows, are actually stored inside of a page. So really, you just have a bunch of sorted data at the front, and then those point to this cell data at the back. So you have these slots, and then they fill up over here. So they are pointers to this free space. So if you go to the next slide, it'll kind of show that. So like you have all these slots here, and they have specific keys. So they're sorted keys. And then they effectively point to this block of memory that you can start allocating and just append to. But you can maintain a sorted order over here for the keys. And so that allows you to store variable length strings or rows or whatever you want in these pages. And so you can just concatenate all these pages together in just a long chain. It's very slow, which is why you actually need something like a B tree. So on the next slide, or this deals with tuples that are actually too big to fit in a single page. So you'll have an overflow. But I guess the next slide is we deal with things like B trees. So B trees are what you might think of as like an index in a database. So it's a large tree structure of pointers that you can say, hey, I'm looking for key 42, and then you start at the top, and then you do a binary search down this tree, and it will give you the exact tuple that you're looking for inside of this tree here. So it's O log n to search and insert and delete. And once you've actually found the keys, you can scan along the leaves. So the bottoms are all sort of connected to each other, and so you can treat it as like a big linked list at the bottom. So I guess next slide kind of will describe this. So you have all these keys in the leaves here, and if you go to the next slide, this is how you would actually insert data into this giant tree structure. So say you wanted to insert 5. You could start at the top and compare at the root, and then you could traverse down the root. So if you kind of click through here, you can see where it falls in. But it also needs to stay balanced. So if you keep going through here, it self-balances. So it'll start to split apart here, and that will insert the key where you actually wanted it and maintain the balancing of the trees. So it'll sort of grow whenever any of these nodes are at capacity. It'll allocate a new node and sort of grow up from there to keep itself balanced. And so the next one is just kind of a repeat, or sorry, it's a removal of the key. So if you want to actually remove from a key, you have to borrow from neighboring leaf nodes until you've compacted the tree. So it'll borrow the 5. It'll then squish those 2 together, right? So it has to borrow that key from its neighbor, and once it's borrowed the key, if the 2 are less than half full, they'll merge together.
What do you mean by borrow? You mean copy?
Yeah, so it'll move it. It'll move it from its sibling, and then it'll compact. And so it'll start to remove keys that are half full. It'll cascade all the way up to the root. So if it has to keep borrowing all the way up to the top, it'll basically compact itself. It'll compact. If it's half full, it'll go up. If this is half full, it'll compact. If it gets to the root and that's a dead root, it'll just remove the root and go with a new root. So it basically compacts itself all the way up whenever it's deleting. So, actually, I don't know why. It's actually not binary. It's not binary plus tree. That's not what it is. I do know what the plus is, though. There's a lot of different B trees, but the plus tree means that like all the data is stored on the leaves at the bottom. The ones that are at the top are just guideposts to help you get to the bottom.
And the bottom is always the same.
The bottom is always so it's balanced, meaning that like if you go to any leaf, they're all the same distance from the root.
But the depth can be.
It can.
The leaves can
Sorry.
like here, all the leaves are just the leaves can be also at other level.
Yeah, so it'll keep growing, right? So as soon as like any of those leaves like fill up, they'll start to split. And so you get deeper and deeper.
Nobody knows what B stands for.
Yeah.
There's a lot of proposals, but actually the authors have never actually said what B stood for.
Yeah.
So, it could be balanced.
The first
Apparently it could even be Boeing. Boeing was involved.
Yeah. Yeah.
Never said.
There's, it's like a total mystery. I don't know. I tried to look it up and I just don't know. But yeah, B trees, they're kind of the heart of the database. And
What does it mean? Balance structure. Oh, I just read it.
that's funny. Yeah, yeah. So this brings me to SmallDB. So it's a SQLite clone, but it's got an emphasis on readability and not going fast. So the thing is that SQLite is really great. Like, you should use SQLite. It does all of this. It implements a database very well. But the thing is that the code is not very friendly to read if you're trying to learn how databases work internally. So the goal with SmallDB is to make a clone of SQLite that's easy to read.
It's actually a virtual machine.
Yeah. So it actually will query its.
Read a virtual machine.
Sorry.
SQL. Yeah. The logic is like a black box virtual machine.
Well, so what it does is the query planner, it'll take a query, it'll parse it, and it'll turn it into its own bytecode, and then it will use that bytecode and optimize it based off of like costs assigned to different scans and operators. But that's really all I know. I don't think I'm going to go that far with like an optimizing compiler or anything.
Yeah, it's a black box.
Yeah. Well, I just mean like if you're reading the code though, it's kind of hard to like follow. Versus like if you have something that doesn't have like a billion little optimizations in it, because that's what SQLite does, is over the years they've just put in like small micro optimizations that might make it run like 0.25% faster, and then another one that goes another 0.25% faster, and it's just like years and years and years of that to like, now you have a code base that's much harder to read, but and that's fine. But that's just not the goal of this. Like, so I just have this project right now with the goal of implementing SQLite that's just easier to read. So say again?
Is open source?
Well, yeah, it's open source. Yeah. But right now, all I have is a simple in-memory pager and a B-tree implementation. So it's like, it's not even really there at all yet. But if you want to follow it or like contribute or something like that, you're welcome to. I guess next slide. These are the things that need to get done. I mean, I've only been working on this thing for about 3 weeks now, so it's like on and off whenever I have like downtime. So like really, I need to implement variable length encoding for the rows right now to store strings. It's pretty much just a glorified key value database. And also, I need to start on a root page schema. So the thing is with a database, like the way that SQLite actually bootstraps itself is it reads the root page, and then it knows the roots of each of the B trees, the B tree for like the schema. So if you actually look at SQLite, there's a if you select star from SQL or SQLite.master, I think is what it is. There's the actual raw SQL code that was used to generate all the tables in your database. And there's a root pointer to that in the root page, the page 0 of SQLite. So I need to have some sort of a root page schema for, that I can use in the future to actually have all those positions to look for. And then I need to start moving things to disk from memory. In my pager, implement deletion, because I don't actually have deletion. It's a little complicated to work with. And then I need free lists in the pager, and a couple other things as well. But yeah, the last slide is just a QR code if you wanted to look at it. and see what's there right now. It's all written in Zig right now.
What's Zig?
It's like a new programming language, like systems programming language.
Oh.
It's pretty much like C with better macros
Oh, okay.
in in a standard library.
Yeah, I just saw SQLite and most of the SQL database are written in C.
They're written in C, yeah. Like Postgres is written in C and SQLite is as well. So, but yeah, I just wanted to go with Zig because it makes working with like packing data into little 4 kilobyte blocks like a lot easier. So.
What inspired you to do this?
Well, so I've been watching like a lot of videos on databases, and I've always just been curious how they work. And
It sounds like a pain in the ass to
sorry again?
It sounds like a pain in the ass to implement as a single person.
As a single person?
Yeah, I mean.
The creator of SQLite did it himself.
Oh, really?
Yeah. Yeah.
Is there anything surprising that you've learned about how databases work that you've learned from this project?
Like really just the storage model is kind of like fascinating to me. I think whenever I start like getting into concurrency control, I'm probably going to want to shoot myself. But like, yeah, I think just learning how everything like works on disk is kind of fascinating. What really blows my mind is like the sheer like size of things that you can store inside of SQLite. And I believe that there's like an inefficiency as well. I think that the way that it actually handles overflow is like wrong.
Huh.
Or maybe I'm just interpreting it wrong or something like that.
Interesting. Okay.
I also claim it's faster than file store for images.
Yeah, that's because it doesn't have to do like a system call to open another file because the file is already open.
SQLite is Microsoft product, right?
No. It's totally open source. I think it's public domain actually.
Okay.
Yeah.
It's under HCP.
Like people like repurpose the like pager and like the shim layer. So like there's like a stack of, at the very bottom there's like the OS, and then right below that's like the pager, which actually like fetches pages for you. So like people will take that pager out and then put their own thing in there. I don't know examples of this, but I can speculate. Like I know that there's definitely people that have traded the OS layer out for like WASM layers so that you can actually like interface with like local storage inside of the browser. But I mean, aside from that, I don't really know what else is going on with that. But yeah. Yeah.
Also, should be someone also wrote a stripped down version of MongoDB in pure JavaScript.
Wow.
Yo.
It runs in the browser, and he
Really?
implemented a B tree for it as well.
Oh, okay.
It's called NEDB.
NODB?
NE.
Okay.
The letters NEDB.
NEDB. Okay. Interesting.
It's probably not that efficient, right? It's troublesome.
Yeah, actually, I looked at the B tree, and it would probably make more sense just to use an array because the size of the database you're dealing with.
Is it all in memory?
Yeah. So
Okay.
the B tree wouldn't actually make it faster, even though he implemented it.
Yeah.
It would have been faster if it was just an array.
Unless you have a massive amount of data in memory.
It's only going to be at most 100 kilobytes.
Oh, okay.
Yeah. Thanks. This is my first like talk, guys. Thanks.
It's a smaller usual problem, but yeah, thank you.
Awesome. Yeah. I think it'd be interesting also to like see if you could like port this into like WebAssembly and like make it work in the browser. It'd be kind of cool.
You mentioned machine learning and models and stuff, so that
Yeah. So I would say a machine learning model is a database just because it is data.
Yeah,
right?
we have nodes and stuff, right?
It is like weights. Like the weights is the database.
Oh, yeah.
Like the database management system would be like how you actually query it, right? That's, I don't know, that's kind of a philosophical thing. I'd say, I don't know.
Did everybody get the QR code?
Yes, I followed. I mean, I started your repo.
Sick, thanks. Yeah.